The talk I'll be giving is on leveraging machine vision to predict the ingredients held within a dish given an image of it. And I don't represent a corporation, so this talk's going to be a little different than the previous two. Um, Really, this is going to be about sort of like the techniques and process we use to accomplish the amount of this task that we did accomplish. So we looked it up, and there hasn't actually been anyone that has ever attempted to do this before. So for a unique undertaking, we decided we needed a unique name for this thing, so we decided to call it the Food Network. I looked it up, and there's not ever been anything that's been called this before. If I were to make a logo for it, it would look like this. So the task is to basically, pull out a list of ingredients given an image, and the task is to come up with an algorithm that can do this. One set of algorithms that have really been successful dealing with image data lately are the convolutional neural network. Here is a diagram of a traditional neural network, which we all know and love. This one has, 3 inputs and 1 output, 2 hidden layers. Each of the arrows represents a weight, and these weights facilitate a linear combination of data that is used as an input for a specific neuron, which then is passed through an activation function, and that is the output to the next set of neurons. We forward propagate information through our network, and we use a loss function to calculate how wrong our prediction is. And you can imagine if we randomly initialize our weights, which we usually do, our prediction is very wrong. The one thing that the loss function affords us is that if we calculate the derivative of this loss function with respect to the weights, and we change the weights just a little bit, in that direction of steepest descent, our prediction gets a little better. This is called gradient descent. What's not immediately obvious is how we input an image into this model. So if we had an image, let's say 10 by 10, one could imagine naively that we could have 100 input neurons. And that sounds good, but really we want this network to be robust to manipulations of the data, maybe taking an image of the same thing from 2 different angles. This approach wouldn't work for that. How are we going to exploit the spatial information used within an image? Enter the convolutional neural network. So here we have the architecture for VGG, which I'll get into later. A convolutional neural network utilizes a set of convolutional filters which calculates the amount that a certain filter is similar to a specific portion of the image. And this is an area around that we call a neighborhood around some center pixel. Not the center of the image, just the center of what we're comparing the filter to at a given time. The way we calculate this is through a matrix dot product. We see when this filter in the center here is compared to the image on the left, and we calculate this dot product, which is just a sum of element-wise multiplication, we get this value. And we do this over the entire image for some number of filters. So it allows us to reuse the information on the filter, or on the image, a number of times. In the case of VGG, it's 64 times. This is a visualization of these filters, and they're kind of trippy, because these are learned. These aren't things that data scientists and machine learning engineers decided would just be the best thing to compare to an image. These are learned. And so when we see something like alternating white and black, it means that some section of the image is very different in this orientation from another part of it in the same orientation that's right next to it, which essentially is just a complicated way of saying that that is an edge of some object in the image. When we see a slow fade from one color to the next, we're calculating some sort of gradual change in color, maybe shading. And so one cannot talk about convolutional neural networks without bringing up the ImageNet challenge. ImageNet is a database of labeled images that they've got like 14 million of them. They have a challenge every year where they try and get people to predict on 1 million of these, or 1,000 different categories. VGG came in second place to Google in 2014. Oxford's Visual Geometry Group are the people that make it. And so we use their model in this task. The difference between ours and theirs is we pop off their classification layer of 1,000 classes, and we predict on the 500 most common ingredients in our data set. This is the architecture of VGG. It runs these convolutional layers over the image, and it does this a number of times, but it's actually very hard to interpret what's going on past the first, so I'm not really going to get into that. Suffice to say, it makes a very dense representation of the image that still contains all of the spatial information, which is great. We feed that into a traditional neural network, if they're at the end fully connected. We propagate it through, we make our prediction, we calculate our loss, and we back propagate and train. That's how we train our convolutional network. So the data we use is scraped off of the website Yumly. You guys might be familiar with it. They claim to have over 2 million images, and we scraped them for 2 million recipes. We scraped them for 1.6 million and 1.1 million images. So we have 1.1 million image recipe pairs. And the website looks like this. You can see in this instance, there is a nice image over there, as well as, thankfully, they separate their recipe lines from their actual recipe process, which made things a little easier. Some of the images we have include, things that are well lit. Well lit, you can see the ingredients held within the image. Seems like great fodder for a convolutional neural network. Some other pieces of data that we have, not that great. Yumly is a recipe aggregator, so it doesn't actually do any quality check for the data that it stores, which is why sometimes we get things like this. There are a lot of instances of recipe images in our database that do not even contain images of food, which was and still is an issue. So you'll also notice that these ingredients, they're not just ingredients, they are amounts and states. And we want to predict if a dish has garlic in it, not if it has garlic powder or minced garlic or a cup of garlic. We want to predict if it has garlic. So we utilized probably the most novel thing that we did in this project, a method to automatically clean these ingredients. So what we did is we took all of them and sorted them by frequency. And what we noticed was that typically in recipes, it is more common over the set of all recipes that people will use an ingredient name with no denomination of how much of it is being used in the ingredient, more so than any one specific denomination. And so onions are, it's more common that in a recipe, people will say onions than they'll say 1 cup or 2 cup or half a teaspoon of onion powder or something like that. So what we did is we created an algorithm that would split these ingredient lines into bigrams and unigrams and search this frequency list from most to least frequent. We split it from bigrams to unigrams from back to front because we kind of noticed that the food is actually usually near the back of the ingredient line. And so we notice here that when we split up this string here, cottage cheese gets a very high score because it's actually a food and it's very high up in our list of sorted ingredients. 4 cups onion diced and salted. All of these things are not ingredients that anyone would ever use except, oh wait, onion is, so it gets a very high score because it actually was near the top of our list. 10-ounce can of garbanzo beans, low sodium. We see garbanzo beans gets a high score, as does beans, but thankfully we weight bigrams a little more, and so even if beans was a little higher than garbanzo beans, we prefer the bigram, and that facilitates the automatic cleaning of our textual ingredient data. Suffice to say, that didn't solve all of our problems. For instance, a spring onion and a green onion are they're the same thing, and no computer would know that unless we utilize something like word embeddings, which we didn't. And so we just went in. Any cool undertaking is going to take some inherently uncool legwork. And we went into our top 1,000 ingredients and reduced things down to a single synonym. Green onions, spring onions, and scallions all became green onions. High-level ingredients like pizza dough, we reduced to like flour, water, salt, olive oil, yeast, because if one pizza recipe uses pizza dough and the other actually has the recipe for pizza dough, that's just going to confuse our network. So we tried to reduce those as much as possible. We trained it for 2.3 days on my consumer NVIDIA graphics card, which it turns out that they're really, really good at matrix multiplication, and everyone who does computer vision trains on these things, on these cards. You'll see that over the course of our training, our loss went down, and it was still going down, and our validation loss didn't actually diverge from the loss. So there's no evidence that we've overfit. In fact, there's evidence that we could have trained for even longer. So it was able to learn some things pretty well. In this precision recall curve, we see that our precision is pretty high when we recall things based on needing a high threshold. So like chocolate, that got a pretty good, it seemed to learn it pretty well. Noodles seemed to learn it pretty well. Kind of learned some other things. It learned tomatoes and sugar pretty well. And paprika and coconut it did not learn. So here, I intended to do a live demo, but that wasn't an option. So here's just a picture from our validation data. The network was not trained on any of these images, and I selected a set of 5 of them, and I didn't choose to or not include any of those 5. So these are unbiased selections. So we see here that our model thinks there's flour, salt, baking soda, etc. Seems to do pretty good on this baked item. Ground beef and vegetable pizza. A lot of things. It didn't get paprika. We see beef, which is nice. Beef was actually harder to learn than I thought it was going to be. Asparagus eggs Benedict with grain-free biscuits and avocado hollandaise. I don't know why I'm reading this. You guys can all read. So, we see, lemon, great. Maybe pepper. It's actually, frankly, impossible to learn different kinds of oils based on the image. So we'll probably end up reducing that. The term's not over yet. We see here an example of kind of a gross image that just looks like a cup of beaten eggs, but it is in fact fresh custard. But it didn't get eggs. Strawberry jam. I think we got all of these things: lemon, strawberry, and sugar. But this isn't even a picture of the thing itself. So it's. Oh well, that's it. Anyone have any questions?